Hello everyone, this is Chinnaiah Kalpana here. In this video, we're going to solve a differential equation using integrating factor. So let's get going. Problem: solve 3x square y power 4 plus 2xy into dx plus 2x cube y cube minus x square into dy equal to 0. So we are given a differential equation of mdx plus ndy equal to 0 form, right? Mdx plus ndy equal to 0 form. For m equal to 3x square y power 4 plus 2xy and n equal to 2x cube y cube minus x square. If the partial derivative of m with respect to y equal to partial derivative of n with respect to x, then we can say that the given differential equation is exact. Otherwise, it is non-exact. So let's find the partial derivatives of m and n. I'll begin with the partial derivative of m with respect to y. We have m 3x square y power 4 plus 2xy, right? So here we need to find partial derivative with respect to y. So we'll treat x as constant. So here in the first term 3x square is constant, and in the second term 2x is constant. So we can write this as 3x square into partial derivative of y power 4 with respect to y plus 2x into partial derivative of y with respect to y, which gives us 3x square into partial derivative of y power 4 with respect to y is 4y cube plus 2x into partial derivative of y with respect to y is 1, which gives us 3 4s are 12 x square y cube plus 2x, right? Let's now find partial derivative of n with respect to x. For n equal to 2x cube y cube minus x square, right? Here we need to find partial derivative with respect to x, so we'll treat y as constant. In the first term 2y cube is constant, so we'll write it as 2y cube into partial derivative of x cube with respect to x minus partial derivative of x square with respect to x. This gives us 2y cube into partial derivative of x cube with respect to x is 3x square minus partial derivative of x square with respect to x is 2x, which gives us 2 3s are 6 x square y cube minus 2x. Now by comparing these two, we can say that partial derivative of m with respect to y is not equal to partial derivative of n with respect to x. Consider the given differential equation as equation number 1. Therefore, 1 is not exact. Since 1 is not exact, so we need to find an integrating factor, suitable integrating factor, in order to reduce the given differential equation to an exact equation. So let's say that given differential equation 3x square y power 4 plus 2xy into dx plus 2x cube y cube minus x square into dy equal to 0, which is considered as equation 1. Since 1 is not exact, we can write this equation as 3x square y power 4 dx plus 2xy dx plus 2x cube y cube dy minus x square dy equal to 0, right? Now let's take x square y cube common from these two terms and x common from these two terms. Okay, firstly I'll write these first term and third term together. Now I'll write the remaining terms. Now we can just take common, x square y cube common from these two terms. We'll get x square y cube into 3y dx plus 2x dy plus, now take x common from these two terms, you'll get x times 2y dx minus x dy equal to 0, right? We can write this as x cube y cube into 3y dx plus 2x dy plus, here you're having x, right, and we don't have any y term. We can write x as x power 1 into 1, since y power 0 equal to 1, so we can just replace this 1 by y power 0, and you can write x as x power 1 into y power 0 or x into y power 0. Okay, this of x power a y power b into my dx plus nx dy plus x power c y power d into py dx plus qx dy equal to 0 form. Consider as equation 2. Equation 2 is of this form, right? Now by comparing these two, we'll get the values of a, b, c, d, m, n, p and q. Since the given differential equation can be written of this form, so here x power alpha y power beta will be the integrating factor. Okay, and here we need to find alpha and beta. Fine. Now let's compare these two equations and find the values of unknowns. We'll get a equal to 2, b equal to 3, c equal to 1, d equal to 0, okay, m equal to 3, n equal to 2, p equal to 2, q equal to minus 1, right? Fine. Since the given differential equation is of this form, it can be written of this form, so here x power alpha y power beta will be the integrating factor. Let x power alpha y power beta be the integrating factor. Multiplying 1 by integrating factor, x power alpha y power beta. X power alpha into y power beta. See, we are given a non-exact equation, so by multiplying it with an integrating factor, it becomes an exact equation. Okay, into equation 1, 3x square y power 4 plus 2xy into dx plus 2x cube y cube minus x square into dy equal to 0. Now we can write this as x power alpha y power beta into first term 3x square y power 4 plus 2xy into dx plus x power alpha y power beta into second term 2x cube y cube minus x square into dy equal to 0, right? Again we can write this as 3 x power alpha x square y power beta into y power 4 plus 2 x power alpha into x y power beta into y into dx plus x power alpha, you are having constant, right? 2 x power alpha x cube into y power beta y cube minus x power alpha x square y power beta into dy equal to 0. If the bases are equal, you can add the powers, right? Since bases are equal, so we'll add the powers, we'll get x power alpha plus 2. Likewise for y power beta plus 4 plus 2x power alpha plus 1 y power beta plus 1 into dx plus 2x power alpha plus 3 y power beta plus 3 minus x power alpha plus 2 y power beta into dy equal to 0. Consider this equation as equation asterisk. Now, this asterisk, equation asterisk will be exact if, see this is of mdx plus ndy equal to 0 form, right? For m equal to 3x power alpha plus 2 y power beta plus 4 plus 2x power alpha plus 1 y power beta plus 1, and for n equal to 2x power alpha plus 3 y power beta plus 3 minus x power alpha plus 2 y power beta, right? This is of mdx plus ndy equal to 0 form for m equal to 3x power alpha plus 2 y power beta plus 4 plus 2x power alpha plus 1 y power beta plus 1, and for n equal to this one. Okay, I'll write it again. Right? This is of m dx plus n dy equal to 0 for m equal to 3x power alpha plus 2 y power beta plus 4 plus 2x power alpha plus 1 y power beta plus 1, and for n equal to 2x power alpha plus 3 y power beta plus 3 minus x power alpha plus 2 y power beta. Equation asterisk is exact if partial derivative of n with respect to y equal to partial derivative of n with respect to x for m equal to this and for n equal to this one. Then partial derivative of m with respect to y for m equal to 3x power alpha plus 2 y power beta plus 4 plus 2x power alpha plus 1 y power beta plus 1 equal to partial derivative of n with respect to x for n equal to 2x power alpha plus 3 y power beta plus 3 minus x power alpha plus 2 y power beta, right? So in the LHS part we need to find partial derivative with respect to y, right? So here x is treated as constant. The first term 3x power alpha plus 2 is constant, and in the second term 2x power alpha plus 1 is constant. If you observe the second one, here we need to find partial derivative with respect to x, right? So y is treated as constant. In the first term 2 y power beta plus 3 is constant, and in the second term y power beta is constant, right? Now we'll write this equation as 3x power alpha plus 2 into partial derivative of y power beta plus 4 with respect to y plus 2x power alpha plus 1 into partial derivative of y power beta plus 1 with respect to y equal to constant 2 y power beta plus 3 into partial derivative of x power alpha plus 3 with respect to x minus constant y power beta into partial derivative of x power alpha plus 2 with respect to x. Now we can write this as 3x power alpha plus 2 into partial derivative of y power beta plus 4 with respect to y is beta plus 4 into y power beta plus 4 minus 1 plus 2x power alpha plus 1 into partial derivative of y power beta plus 1 with respect to y is beta plus 1 into y power beta plus 1 minus 1 equal to 2y power beta plus 3 into partial derivative of x power alpha plus 3 with respect to x is alpha plus 3 into x power alpha plus 3 minus 1 minus y power beta into partial derivative of x power alpha plus 2 with respect to x is alpha plus 2 into x power alpha plus 2 minus 1, which gives us 3x power alpha plus 2 into beta plus 4 into y power beta plus 4 minus 1 plus 3 plus 2x power alpha plus 1 into beta plus 1 into y power beta equal to 2y power beta plus 3 into alpha plus 3 into x power alpha plus 3 minus 1 plus 2 minus y power beta into alpha plus 2 into x power alpha plus 2 minus 1 is plus 1. This gives us 3 beta plus 4 into x power alpha plus 2 y power beta plus 3 plus 3 2s are plus 2x power you'll have into b plus 1 into x power alpha plus 1 y power beta equal to 2 alpha plus 3 into x power alpha plus 2 y power beta plus 3 minus alpha plus 2 into x power alpha plus 1 y power beta, right? So here, by equating the coefficients of x power alpha plus 2 y power beta plus 3, you'll get one equation, and by equating the coefficient of x power alpha plus 1 y power beta, you'll get another equation. So let's equate them. Equating the coefficient of x power alpha plus 2 y power beta plus 3 gives 3 times beta plus 4 equal to 2 times alpha plus 3, right? Which gives us 3 beta plus 12 equal to 2 alpha plus 6. Or we can write this as 2 alpha plus 6 equal to 3 beta plus 12. Now bring this 3 beta to LHS and take this 6 to RHS. We'll get it's 12, okay? We'll get 2 alpha minus 3 beta equal to 12 minus 6, which gives us 2 alpha minus 3 beta equal to 12 minus 6 is 6. Consider as equation number A. Equating the coefficients of x power alpha plus 1 y power beta, which gives us 2 times beta plus 1 equal to minus of alpha plus 2, which gives us 2 beta plus 2 equal to minus alpha minus 2, right? Now bring these two terms to LHS, or just bring minus alpha to LHS and take this 2 to RHS. We'll get alpha plus 2 beta equal to minus 2 minus 2, which gives us alpha plus 2 beta equal to minus 4. Consider as equation number B. Now by solving A and B, we'll get alpha and beta. Let's see that. We have equation A, 2 alpha minus 3 beta equal to 6, and equation B, alpha plus 2 beta equal to minus 4. Now we need to solve A and B, right? So here I'll try to cancel the terms involving alpha. So if you compare these two, here you're having 2 alpha and here you're having alpha, right? So you need a 2 here. What we'll do is we'll just multiply equation B by 2. Now solving A and B. Equation A will remain same and equation B is multiplied by 2. You'll get 2 alpha plus 2 2s are 4 beta equal to minus 2 4s are 8. Change the signs. Here plus 2 alpha minus 2 alpha gets cancelled. Minus 3 beta minus 4 beta gives minus 7 beta equal to plus 6 plus 8 is plus 12. Sorry, plus 14. Right? From this we'll get beta equal to 14 by minus 7 or minus 14 by 7, which gives us minus 2. Therefore, beta equal to minus 2. Right? Fine. Now let's put this beta value in equation A. We have equation A, 2 alpha minus 3 beta equal to 6. Let's take this minus 3 beta to RHS, then you'll get 2 alpha equal to 6 plus 3 beta. Now substitute the value of beta. Since beta equal to minus 2, you'll get 6 plus 3 into minus 2, which gives us 6, minus 3 to the 6, which is 0, right? From this you'll get alpha equal to 0. Therefore, alpha equal to 0. See, or you can substitute the beta value in equation B. Let's check it in equation B. Alpha plus 2 into beta equal to minus 4, which gives us alpha minus 4 equal to minus 4. From this you'll get alpha equal to minus 4 plus 4, which is equal to 0. Again you'll get alpha equal to 0, right? So the value of alpha is 0 and beta equal to minus 2. Now we got the values of alpha and beta. Now we need to find the integrating factor, actual integrating factor which is suitable to our problem. Okay. Therefore alpha equal to 0 and beta equal to minus 2. Integrating factor x power alpha y power beta equal to x power alpha value 0, y power beta minus 2, which is equal to x power 0 is 1 into y power minus 2, which gives us y power minus 2. Right? So therefore, y power minus 2 is the integrating factor to our problem. Now multiplying this integrating factor to equation 1. By multiplying this integrating factor to equation 1, the equation 1 will be reduced to an exact equation. Okay, multiplying y power minus 2, which is an integrating factor, to equation 1. Then you'll get y power minus 2 into integrating factor into equation 1, 3x square y power 4 plus 2xy into dx plus 2x cube y cube minus x square into dy equal to 0, right? This gives us y power minus 2 into 3x square y power 4 plus 2xy into, you can just multiply directly to all the terms or you can just write one more step. Okay. This becomes 3x square y power 4 into y power minus 2 plus 2xy into y power minus 2 into dx plus 2x cube y cube into y power minus 2 minus x square y power minus 2 into dy equal to 0. Or we can write this as 3x square, add the powers, you'll get 4 minus 2 plus 2xy. Here you are having power 1 minus 2, add the powers into dx plus 2x cube y power 3 minus 2 minus x square y power minus 2 into dy equal to 0. And this you'll get 3x square y square plus 2x y power 1 minus 2 is minus 1 into dx plus 2x cube y power 3 minus 2 is 1 minus x square y power minus 2 into dy equal to 0. Since y power minus n can be written as 1 by y power n, so we'll write y power minus 1 as 1 by y and y power minus 2 can be written as 1 by y square. Then this becomes 3x square y square plus 2x by y into dx plus 2x cube y minus x square by y square into dy equal to 0. See, you are having x into y inverse, right? You can write this y power minus 1 as 1 by y, which becomes x by y. So you'll get 2x by y here, since you're having constant 2 here. And here you're having x square y power minus 2, since you can write y power minus 2 as 1 by y square. So this becomes x square by y square. Okay. Now consider this equation as equation number 3, which is of mdx plus ndy equal to 0 form. This is of mdx plus ndy equal to 0 form for m equal to 3x square y square plus 2x by y and n equal to 2x cube y minus x square by y square. Okay, so we have reduced the given differential equation to a differential equation by multiplying the given equation with an integrating factor. So it has to be an exact equation. So let's check it out. So if the partial derivative of m with respect to y equal to partial derivative of n with respect to x, for m equal to quotient of dx and for n equal to quotient of dy, then we can say that equation 3 is an exact equation, that is the reduced equation is an exact equation. So if it is an exact equation, then using the general solution of exact equation procedure, we'll find the general solution to equation 3, which will be the required solution to equation 1. So let's see that. Now I'll begin with the partial derivative of m with respect to y. For m equal to 3x square y square plus 2x by y. Since we need to find partial derivative with respect to y, so here x will be treated as constant. For that I'll write m as 3x square into y square plus 2x into 1 by y. Okay. Here in the first term 3x square is constant, in the second term 2x is constant. So we can write this as constant into partial derivative of y square with respect to y plus constant into partial derivative of 1 by y with respect to y, which gives us 3x square into partial derivative of y square with respect to y is 2y plus 2x into partial derivative of 1 by y with respect to y is minus 1 by y square, which gives us 3 to the 6 x square y minus 2x by y square. Okay, therefore partial derivative of m with respect to y is 6x square y minus 2x by y square. Now let's find partial derivative of n with respect to x. Dou by dou x of n 2x cube y minus x square y square. So here we need to find partial derivative with respect to x. So here y is treated as constant. Okay. For my convenience, I'm going to write this as 3 2y into x cube minus 1 by y square into x square. Okay. In the first term 2y is constant and in the second term 1 by y square is constant. So we can write this as 2y into partial derivative of x cube with respect to x minus 1 by y square into partial derivative of x square with respect to x. This gives us 2y into partial derivative of x cube with respect to x is 3x square minus 1 by y square into partial derivative of x square with respect to x is 2x, which gives us 2 3 is a 6x square y minus 2x by y square. Right? Therefore, partial derivative of n with respect to x is 6x square y minus 2x by y square. Right? Now by observing these two, we can say that partial derivative of m with respect to y equal to partial derivative of n with respect to x equal to 6x square y minus 2x by y square, which shows that equation 3 is an exact equation. Okay, therefore equation 3 is an exact equation. So we have reduced the given differential equation to an exact equation. Now we'll find the general solution to equation 2 using the general solution formula of exact equation. Finally, it results to a general solution or the required solution to the given differential equation. Fine. We know that the general solution to an exact equation is given by integral mdx treating y as constant plus integral terms of n free from x into dy equal to c. Okay, so here our exact equation is equation number 3, and for m equal to 3x square y square plus 2x by y, and for n equal to 2x cube y minus x square y square, we'll find these two integrals to find the general solution to equation 3. Okay, I'll begin with the first one. Integral m dx treating y as constant equal to, for m equal to 3x square y square plus 2x by y into dx. Here y is constant. Okay, so in the first term y square is constant and the second term 1 by y is constant. So we'll write this as 3y square into integral x dx. It's x square, right? So you'll get x square dx plus 2 by y. Here 2 by y is constant. Okay, you can write 2x by y as 2 by y into x, where 2 by y is treated as constant. You'll get 2 by y into integral x dx, which gives us 3y square into x square. Integral x square dx is x cube by 3 plus 2 by y into integral x dx is x square by 2. Right? This gives us x cube y square plus 1 by y into x square gives x square by y. Okay, so the result obtained from the first integral is x cube y square plus x square by y. Now coming to the second integral. Integral terms of n free from x into dy. So now observe n. So in both the terms we are having x, right? There is no such term which is free from x. So integral terms of n free from x is 0. So the result obtained from the second integral is 0. Therefore, the general solution to the transformed equation, that is equation 3, is integral m dx treating y as constant plus integral terms of n free from x into dy equal to c. This is equals to, result obtained from the first integral is x cube y square plus x square by y, plus result obtained from the second integral is 0 equal to c. Now take the LCM of these two, you will get x cube y cube plus x square by y equal to c. Or you can write this as x cube y cube plus x square equal to c into y. You will just take this y to RHS, then you will get cy. Okay, therefore x cube y cube plus x square plus c is the required solution to our problem. Therefore, x cube y cube plus x square equal to cy is the required solution to equation 1 or to the given differential equation. So this completes the problem. Well, we have seen a problem from integrating factor in this video. I hope you'll understand. We'll see you in the next video. Until then, bye bye.